All right, lesson 4.5. As we open up this bell ringer, this is very similar to the ACP problem for 4.4, whereas on 4.4 we were looking at the cosine graph. This packet opens up showing us a diagram or an image of the first and fourth quadrants of the sine graph, y equals sine x. It says here for number 1, find the coordinates that describe the maximum and minimum values for y equals sine x. And specifically, though it doesn't say it, I'm talking about the positive domain from 0 to 2 pi. I'll do the Desmos symbols here from 0, if you remember the squigglies, from 0 to 2 pi. And then over here on number 2, it says find the coordinates that would describe the maximum minimum values for the graph of y equals sine x if the domain was restricted from negative 2 pi to 0. So on your second slide, I actually gave you a better image to work with. So I'm going to come over to the calculator here and type in sine x so we can remember what this graph looks like. There was cosine, here's sine. How do you describe this shape? Wave. Yeah, it's a wave. And so this would be no different over here. If you want to do on your packet, line it up like this and draw your wave. I'm trying to do the best I can. It would look something like this. And truthfully, if we wanted to start making markings, this point right here, what would that be on the x-axis? I hear negative 2 pi. We're on the right track thinking negative, but it's not 2 pi. It'd be negative pi, perfect. And what would this point be right here? That's negative 2 pi. Okay, what if I wanted to be more precise? Coming over here, this is 0. This is 0. That's 1 pi. What's halfway between 0 and 1 pi? Okay. Okay, as I was saying, what's halfway in between 0 and 1 pi? Pi over 2. Yeah, half a pi. That is half a pi if we want to leave that. And if this is half a pi or 1 pi over 2, that's 1 whole pi. What would this be? I hear 2 pi over 3. That's a good guess, but that's not. I think that's 1 half. That's 2 halves. This would be 3 halves. So 3 pi over 2. There you go. You were just talking dyslexic. That's all it was. You knew what you were doing. Okay, so when we come over here, we can label the x values as negative pi over 2. That's a negative pi, and this is negative 3 pi over 2. Okay, so really what this problem is asking you for is number 1, to find the coordinates that would describe the maximum minimum on the right side. So remember that would be like this point here. This would be a maximum. You need to find that coordinate and the coordinate for the minimum. And then it also says for number 2, find the coordinates that would describe the maximum minimum on the negative side. So you'll then come over here and find this minimum and this maximum. I'll let you do that on your own. But now you're off to the races. One thing for clarity is number 1 is talking about the right side. So number 1, you're looking for these values over here. This is number 1. And remember, points go in the form of x comma y. So as you find your coordinates, you're looking for x followed by the y value. And then this is number 2 on the left side of the graph. So number 1, that's number 2 over there. Today, we are specifically going to look at graphs now of tangent and cotangent, cosecant, secant. That's what we're going to look at. So first off, the thing I want to draw your attention to is these do not look like waves. So sine and cosine look like waves. We saw that last class. Sine and cosine graph, they look like these waves. Together, they kind of look like the DNA double helix that you learn about in your science classes. Well, the other graphs, let's talk about tangent. Y equals tangent looks like this. How would you describe those? Do you remember the name first semester, what we called that? No, there are infinite discontinuities. Very good. That's where they break and go to infinities. These are a whole bunch of S curves. A whole bunch of S curves separated by infinite discontinuities, vertical asymptotes. Very good. That would be tangent. And I'll go ahead. I put T. I didn't mean to put T there. I put Y equals. And here is cotangent, if you want to know its reciprocal. Notice they're very similar. You see how similar those two graphs are? See how those are similar? Okay, that's tangent, cotangent. But the sines and cosines, their graphs do not look like sine and cosine at all. They're reciprocals. I'm sorry. Here's CSC. Does that look like the sine curve at all? No, the reciprocal for sine doesn't look like it at all. It looks like a bunch of parabolas back and forth, whereas the minimum of this parabola happens to be the maximum of sine's wave, and the maximum of this parabola happens to be the minimum of sine's wave. So that's really the only thing together. And then here is cosine's reciprocal secant. It also looks like a collection of parabolas, and the same idea. Cosine being the wave where the maximum of the wave is the minimum of that parabola, and the minimum of this wave is the maximum of this parabola. So that's just kind of how they look. You can see all 6 graphs. Notice that sine and cosine were the never-ending waves, no breaks whatsoever. All the other four functions have vertical asymptotes. They will have vertical asymptotes. Today, we're going to spend a lot of that time talking about these vertical asymptotes. So the first question might come up, why do the other 4s have vertical asymptotes? Well, I'm going to show you from our cheat sheet. Looking on the cheat sheet, and specifically at the 6 trig functions, sine, cosine, tangent, cosecant, secant, cotangent. I want you to look at those and tell me, sine and cosine, what are they being divided by? Look at your paper, your cheat sheet. What is sine and cosine being divided by? H. Okay, on the bottom right of yours, down here on the bottom right, I gave you 2 rules. I want you to read off. What does rule number 2 say? H is always positive. The reason sine and cosine don't have any breaks is to have a break, you have to be dividing by 0. You have to break a math rule. If H is always positive, could it ever divide by 0? No, because 0 is not a positive number. Since H is always positive, they never get divided by 0. Check out the other 4 functions. Do we have ever, again, an H in the denominator on any of these 4? No. And so tangent can have a break when x equals 0. Cosecant can have a break when y equals 0. Secant will also have a break, just like tangent, when x equals 0. And cotangent, just like cosecant, will have a break when y equals 0. There are vertical asymptotes. This slide right here is just telling you that tangent's graph will look like S-curves, and it'll have a whole bunch of breaks, and that is any time the x equals 0 in the denominator. So I'm going to give you steps on how to find that, but here's how we begin. And this is telling you about the period of a tangent. Oh, this is important. For sine and cosine, one period means a full lap around the circle. How many radians are there to get all the way around the circle? 2 pi. It takes 2 pi to go all the way around. Tangent's not that way. Tangent repeats itself every 1 pi. And if you're going, why is that the case? Well, here's the case. This is the reason why. Sine does not repeat itself after 1 pi. Check out sine. Sine goes like this. And I'm just going to deal with positives and negatives. Sine is what letter? X or Y? Y. Okay. So if you start in the first quadrant, sine is positive because y is positive. If you look at the second quadrant, sine is also positive because y is positive. If you go around, this is 0, this is pi over 2, this is 1 pi. Okay, starting at after 1 pi, when you get to the third quadrant, you find out that sine is now negative. Did it repeat 1 pi away? I have positive, positive. Did it repeat here? No, it changed. It went sine is negative and sine again is negative, going from there around. So it doesn't repeat until you go a full 2 pi. Once you go to 2 pi, it repeats. So it goes positive, positive, negative, negative, positive, positive, negative, negative. It doesn't repeat until it makes a full circle around. It takes 2 pi's. Cosine's the same way. If I wrote out cosine, stay with me. Don't fall asleep here. This is important that you grasp this. Cosine deals with which letter? X, Y, or H? I mean, X or Y. Sorry. X. So would cosine be positive or negative in the first quadrant? Positive. What about the second quadrant? Negative. So this one's looking like it might be repeating. But you come over here and guess what you find out in the third quadrant? It's negative. So it doesn't repeat. It's positive, negative. Now we have another negative. Come over here. What can you tell me about cosine? Positive. Again, you got to go a full 2 pi to have it repeat. It goes positive, negative, negative, positive, positive, negative, negative, positive. It doesn't repeat after 1 pi. It repeats after 2 pi. Okay, so now we finally come to tangent. Sine is y, cosine's x. Tangent, you're going to learn. You know it's y over x. You're going to learn tangent is simply sine divided by cosine. That's what tangent is. It's sine divided by cosine. So what's a positive divided by a positive? Positive. So tangent's positive here. What about over here? What is a positive divided by a negative? Negative. Now, finally, I'm getting somewhere. When I come to the third quadrant, what's a negative divided by a negative? Positive. And finally, fourth quadrant, a negative divided by a positive is negative. What happens with tangent after 1 pi? We have positive, negative, positive, negative. You see how it's already repeating? It repeats as early as 1 pi. So this is just saying the period. So for anything in the sine family or cosine family, the period is 2 pi. 2 pi for sine, cosine, cosecant, and secant. That's not how you spell secant. Secant. There you go. But for tangent, cotangent, the period is 1 pi. So tangent family has 1 pi period. All others, the sine and cotangent, the sine and cosine family, the period is 2 pi. So tangent repeats and cotangent repeats after 1 pi. Okay, with that, we are going to find some vertical asymptotes. Today's day is all about finding the asymptotes. Remind me, first semester, if you're going to have a break in the domain, like an asymptote, that means you're dividing by some number. What do you divide by to have a break in the graph? 0. We're going to be solving where we're dividing by 0. So today I'm going to break this down into 4 steps. It's going to be the same 4 steps all day long. Example 1a says this: locate the vertical asymptotes and sketch the graph of y equals tangent x divided by 3. So there's going to be 4 steps. The first step is this. Write out your trig ratio. I'm going to just call it trig ratio. So on this case, what trig function are we using? Tangent. So I'm going to be ready. I'm going to call a lot of names today. So Anna E, I want you to look on the cheat sheet. We're using tangent. What ratio do you have for tangent? Y over x. So step 1 says write out your trig ratio. Step 2, and I'm going to be writing step 2 off to the side every time. So I'm going to write it right here, and then I'll follow down below after. Step 2 is set the denominator equal, oh, no, I'm sorry, not set, find where the denominator equals 0. Find where the denominator equals 0. And so here, and we're going to use our unit circle for this. We want to find out where x equals 0. So I'm going to say x equals 0 at, and I'm going to look on our unit circle where x equals 0. So at this stage, if you have this in front of you, that'd be great. Use your cheat sheet. And again, if you're later on looking at this at home, you can go through Clever and then resources and click on unit circle to pull this open. I want you to look at the x value. So you're only looking at x's. Where's the first x that you see as a 0? What radian amount? Don't give me the degrees. Give me the radians where you first see an x that equals 0. Pi over 2. So step 2, you're going to say x equals 0 at pi over 2. Now here's what that means. Tangent has an asymptote at pi over 2 if it had 0 transformations. With 0 transformations, tangent's asymptote, first asymptote, is at pi over 2. We're going to have transformations. So step 3, I want you to apply horizontal transformations. Apply horizontal transformations. And I'm going to do a little order. If it matters, it won't always matter, but if it does, you first do the C, and then secondly, you do the B value. You might be like, what is this talking about? Remember how the form of the equation is A tangent bx plus c plus d. You first do the c and then you apply the b transformation. So first c, then b. That's the order for transformations here, if it matters. This problem won't matter because I only see one transformation. So here's how to find our vertical asymptote. We're going to start with x equals pi over 2. X equals pi over 2. I got that from step 2. I want to apply my transformations. Looking at this, I'm looking at my value here. I see x is being divided by 3. It's with x. Is x a liar or a truth teller? Liar. Liar. So you're going to apply the opposite of what you see. What's the opposite of dividing by 3? Multiply. We need to multiply this by 3. So when I multiply by 3, I'm just going to draw an arrow over here. It's going to be x equals 3 pi over 2. Now, underneath it, I'm going to say this is the first asymptote. That is your first vertical asymptote. I think having that note will help you process as I go on what we're actually doing. So on this graph, this right here is the first asymptote. This one is the first asymptote. I want you to notice, where is this dotted red line cutting through the x-axis? What's the x value right there? 3 pi. You see how it says 3 pi over 2? You see how our value right there says 3 pi over 2? That's what we just found right there, that first asymptote is at 3 pi over 2. Now, does this graph only have one asymptote? It has more. And so to find those, it's kind of like doing a period. It's not exactly. And so on this one, I'm just going to call it the other asymptotes is all I'm going to call it. To find your other asymptotes, what you will do is you'll take your pi, you'll take pi, and you'll do the opposite of b. Apply, I'm going to put that in parentheses here. Apply b transformations. So only the b. That's the only thing that matters on step 4 is if there's a b. The b is anything connected to the x. Remember, there it is right there. Anything connected to the x. So what does this actually say to do? The b. What's it saying to do? Divide by 3. Is that a truth teller or a liar? Liar. So Maria, what am I supposed to do if it says divide by 3? Multiply by 3. So what I'm going to do is take my pi and multiply it by 3. So it's just 3 times pi. What that means is every following asymptote is 3 pi away from the other. So like that would be 3 pi to the left. This would be 6 pi to the left, meaning 3 pi, another 3 pi, another 3 pi. You just keep going 3 pi's. Or going forward, this would be 3 pi to the right. Now you might be looking at the numbers saying that doesn't make sense. It does. I'll show you why. But for our final answer, here's what you'll do. You'll take this and you'll say x equals 3 pi over 2, what we originally had, plus, and the way they'll write this is 3n pi. That n means you can do it as any number of times. So they'll do n ez if you're an Alex, n ez. What that means, n ez, what that practically means is n is an integer. Where n is an integer. That just means a whole number, positive or negative. Where n is an integer. You don't have to write that, but that you do need the NEZ. Okay, so that's a whole lot to start off one lesson. Now here's the good news. We don't add anything to this the whole rest of the lesson. It is this on repeat, the whole packet. So let me explain to you a little bit more in depth what we're doing, but using a visual approach this time. I'm going to go to Desmos, and I'm going to graph this. Let me limit this so I can see the page. I'm going to graph y equals tangent, and whatever you're doing, don't zone out. This will be really helpful for you, I think, to see it. So on this graph, if you just visually look at it, would you say this has one break or multiple breaks? It has multiple breaks. And if I zoom out, you can see it's an infinite number of breaks. You see how there's just an infinite number of them? They just keep occurring. Okay, what we determined is that first break occurred at x equals pi divided by not pi divided by 2, I'm sorry, 3 pi divided by 2. We said 3 pi divided by 2 was the first break. I'm going to change this to be red and a dot dash line. Tell me, does the red line separate those two S curves, or does it intersect one S curve? Like, is it in the right spot or the wrong spot where I currently have it? It's in the correct spot. Okay, so then we went to step 4, and to find the other asymptotes, we found out you start with pi, and then you apply a transformation, which this one said divide, it's a liar, so we multiply. That means to find all others, 3n pi will give you all others, where n is an integer. What does n as an integer mean? A whole number that's not a decimal. It can be positive or negative. So watch what happens as I change my n. So you see where the asymptote is right now? I'm going to change n to 1. What just happened to my asymptote? It moved 1 to the right. What if I change it to 2? What do you think it's going to do next? It's going to show you my next asymptote. And 3 would be here. There's 4, 5, 6. You see how it's showing you all these asymptotes going out? And it would be the same for the negatives. If you went, let me go back to 0. So that's where we started from, 3 pi over 2. Now, if I went negatives, it just shows me the asymptotes going to the left. There's that one, and so on and so far. Okay, so now you see how this second, when we found the first asymptote at 3 pi over 2, you see how the textbook, or not this image says the next one's at 9 pi over 2. That's because they got a common denominator. Check this out. If I went and typed in right here, I'm not going to type in the pi this time, 3 over 2, and then added 3 times 1, and I'm going to ignore the pi and change the fraction. You see how that says 9 over 2? That's because it does, though it doesn't look like it, 3 pi over 2 plus 3 pi is actually 9 pi over 2. The dickens, you say. It is. I'll show it. I'll prove it. If I took 3 pi over 2, over 2, and I added 3 pi. You learned adding fractions a long time ago, so long ago that many of you forget how. If you're going to add fractions, you need to have a common denominator. So you would say 3 pi over 2 plus, instead of 3 pi, I'm going to change this to 2 times 3 pi. What is 2 times 3 pi? 6 pi. So now I have 9 pi plus 6 pi for the numerator. I said that wrong. I have 3 pi plus 6 pi. What's 3 pi plus 6 pi? That's 9 pi over 2. And you can see the math is right. There's no error in the textbook. That's how it's supposed to look. 3 pi over 2 plus 3 pi is actually 9 pi over 2. I know it didn't seem like it, but that's because we added 6 pi over 2, which is 3 pi. And so that's how you get that. So that was a lot. Would you agree that's a lot? Before I have you do one, I'm actually going to do a couple more, and then we're going to go back and do the CWL. So I'm going to skip your problem just for a moment. We'll come back to this problem. But before I make you do one, I'm going to do 2 more. Okay, so looking back on your notes, I know you're going to have to kind of be flipping back and forth. Step 1. Do you remember what step 1 was? The trig ratio. Now, which trig function are we using this time? Tangent. And the first few problems are tangents, but then after, they'll start randomizing them the rest of the lesson. So when you look in your cheat sheet, sine is y, cosine's x, tangent is y over x. So put y over x. That is step 1, the trig ratio. Step 2. Do you remember what I wrote for step 2? Find where, and I'm just going to say denom this time, denom equals 0. So we want to know, in this case, x is the denominator, where x equals 0. X equals 0 at, use your cheat sheet. Where does x equal 0 at? Same spot as last time because it's tangent again. X has a 0 at pi over 2. So put pi over 2 there. Now what that means for tangent is that if it had no transformations, its asymptote would occur at pi over 2. Do I have transformations in my problem? Yes, so it's probably going to be shifted somewhere or changed. So step 2 is just that. I think did I write it as apply horizontal transformations? Is that how I wrote it? Apply horizontal transformations. And remember what I told you, if there is a B and a C, you do C first, then B. So on this problem, I'm going to start with x equals pi over 2. That's what I'm starting with. I'm starting with x equals pi over 2. If you're wondering why x, is it because this says x? No, it's not because this says x. It's because a vertical line takes the equation x equals. That's why. We're finding a vertical line, an asymptote. So it's going to be x equals no matter what on this stage, no matter what this variable is right here, because that's going to change for different trig functions. So step 3, excuse me, I wrote as 2 there. Step 3 will always say x equals. Step 3, x equals, here's our number value, pi over 2. What horizontal transformations are occurring that time? Remember, horizontal just means on the inside. What does it say to do on the inside? Divide by 4. Juan, is that a truth teller or a liar? Liar. It's a liar. So what's the lie? If it says divide by 4, what should we do? So take this and multiply it by 4. So I'm hearing 4 pi over 2. Could we simplify 4 pi divided by 2? It'll equal 2 pi. That means our first asymptote, I'll write the answer over here. The first asymptote should occur at 2 pi. Look on the graph. Do we see one at 2 pi? Yes. Yeah, that's x equals 2 pi. That right there is our first asymptote. That's like basically what I'm saying by that is later, that means where n equals 0. That's where n would equal 0. That's the first one. So if you want a note for that, that's the first asymptote. First asymptote. Now, how did I write out step 4? What did I call it? Other asymptotes? Is that what I wrote? Yeah. Other asymptotes. Okay, so how you do this one is you're going to take pi, and if there's a b value, you do the opposite of it because, again, it's a liar. B is the one that's connected to x. It either multiplies or divides by x. It doesn't add it. It doesn't subtract it. That's C. B either multiplies or divides the x. Do I have a b on this problem? Yes, we do. What does it say to do right here? Divide by 4. What's the opposite dividing by 4? You're going to multiply by 4. That doesn't simplify. So the final answer here is you will put it together. So the answers are always this plus this together. And you throw in it the letter n. So it'll be 4n pi, comma, where n is an integer, n-e-z. I'm going to do a double z. That's my answer. And that's where n is an integer. That's what that means. N is a whole number, but it could be negative or positive. That's where that means. N is an integer. N is an integer. Okay, I'm going to make sure this is correct. You don't have to do this every time, but I think it'll be good for you just to see what's happening each time. So I'm going to go to my calculator and check this problem. So I have y equals negative tangent divided by 4, or x divided by 4. There's my graph. We think the first transformation occurs at 2 pi. Does that appear to be an asymptote there? Does that appear to be correct or incorrect? If you're like, what would incorrect look like? This would be incorrect. Do you see how that cuts right through the middle of the blue graph? It's not supposed to do that. It's supposed to separate the pieces. That would be incorrect here because it's cutting through. We said it's 2 pi. 2 pi. Does that separate it perfect? Okay, that's the first asymptote. What we're saying is the other ones occur at 4 pi away. So let's do a little mental math. If this is 2 pi and you're going to add 4 pi, what's 2 pi plus 4 pi? 6 pi. So that's why this next asymptote is at 6 pi because this is 2 pi plus 4 pi. 2 pi plus 4 pi equals 6 pi. And so that's why you get that one there. And I can do it here by doing 4n pi. And you would say n equals, you got to get this slider going. I'm just going to do -20 to 20, and it's got to be a whole number. That means a step of 1. Step of 1, like that. And so check it. As I zoom out, does this separate? Is this perfect? Is this hitting every single asymptote? Yes. So we did it correctly. All right. So that's what we're doing there. So making sure you're all following along with me. When you look at an answer like this, what's the front number referring to? Okay, I heard it once over here on the other side of the room. Let's go. Daryl, do you know what this front value is referring to? That would be this value that gets us a 0. What does that first value find? The first asymptote. Good. Okay. Now, Francisco, the part with the n, what is that finding?
How long it takes to get another asymptote.
That's right. And so if n is 1, it's how long it takes to get to the first asymptote. If n is 2, how long it takes to get to 2 asymptotes down. You're right. I'm saying that. Perfect. Okay, I'm going to do one more, and then I'll let you do some DOLs here. All right. I'm going to do one more, and then you're going to try. So step 1. If you're looking for vertical asymptotes, what's step 1? Peyton, what do you have for step 1?
Trig ratio.
Yeah, your trig ratio. We first find the trig ratio. So for tangent, again, we have another tangent. Sine is y, cosine's x. Cheat sheet says tangent is y over x. So we have y over x here. Jada, what do you have for step 2? Not common denominator, but
X equals.
Find where your denominator. There you go. Find where denominator equals 0. And so we need to, for tangent, you need to know where x equals 0. Because that's what's in the denominator. So where does my x equal 0? Where's the first occurring spot? Pi over 2. So it would be pi over 2. Step 3, you take that value. We're going to say, actually, what do we call step 3? Apply horizontal transformations. And remember, if you have a B and a C, you do B first. You do C first and then the B value. That's the order you go in.
So if it's tan, it's always going to be pi over 2.
Yes, because it's always going to be x in the denominator, and that's where x equals 0. You're correct in saying if it's tangent, it's always pi over 2. Okay, so this one, I start with x equals pi over 2. That's where I start, and now I apply transformations. On this one, I see a C. The C says to add pi over 2. What's the opposite of adding pi over 2? We should subtract pi over 2. This will be nice, easy math here. 5 minus 5 is 0. 10 minus 10 is 0. What do you think pi divided by 2 minus pi divided by 2 is going to equal? 0. That means my first asymptote occurs at 0. That is the first asymptote right there. That's what we just found. The first asymptote is at 0. Check your picture. Does the first asymptote occur at 0? Well, it doesn't have it on there, but I'm going to add it. Do I have an asymptote at 0? Better believe it. X equals 0 is an asymptote. Right there, that is an asymptote. So that's good. All right, fourth step. To find the other asymptotes. Other asymptotes. What value do I begin with always? Pi. And then you do the opposite of b to it. So I look up here. What's my b in this problem? It's the value that is connected to the x. It's technically 1 times. What's the opposite of multiplying by 1? Dividing by 1. You would divide this by 1. Is pi divided by 1 anything? That's just pi. So to get your answer, you put those together. That means every other asymptote is pi away from the previous. They're all pi apart. So check it. Is this one is 0 plus pi? What does 0 plus pi equal? Pi. Same thing, 0 minus pi. 0 minus pi would just be negative pi. So you can see we did it right. And so the way you write your answer is you take your answer from here, x equals 0, and then you would say plus, and you put an n in front, n pi. This one's a little trickier. When you add by 0, I say trickier, it's not tricky. It's just another thing we got to write. When you add by 0, does that change the problem? No. So you'd actually write this answer as n pi, comma, n is an integer, n-e double z, n is an integer. Yes. Example 1 you were looking at? What about example 1? Okay, perfect. I want y'all to pause this, or I'm going to pause the video here in a second. I want y'all to go work through your same 4 steps to do DOL number 1. And then once you do that, move on to DOL number 2. I'm going to cover mine up here in a second. Well, I'll leave them up for the video. But if you're listening, just pause this. Everybody else do DOL number 1 and then try DOL number 2. All right, so once you get your answer here, let's jump on over to DOL number 2, and I want you to try this problem now. You can pause the video for time to complete. All right, now let's take a look. We've been looking at a lot of tangents. What we're going to find out is it doesn't matter what the trig function is. We'll have the same 4 steps. So moving on, here's cotangent. Notice cotangent's graph looks very similar. They've left off an asymptote here. When I add it in, they left off that asymptote. Cotangent looks very similar to tangent, except it's decreasing instead of increasing on its S-curve. So let's start with example 3 here. It says locate the vertical asymptotes and sketch this graph for cotangent of 2x. So step number 1, instead of writing it out, I'm just going to ask you, what is step number 1? Trig, I'll write it out. Trig ratio. So the trig ratio for cotangent, look at the cheat sheet. I always say sine is y, cosine's x, tangent is y over x. I don't ever say cotangent. What is cotangent? X over y, which means step 2 for the first time today is going to look different for us. Step 2 is no longer going to be where x equals 0. Step 2 is now going to find, when you find where the denom equals 0, find where denominator equals 0. We're now going to look for where y equals 0. And so when you look on this, I heard pi, that's true. Y is 0 at pi, but there's an earlier occurring one. The very first one that occurs is at 0. Y equals 0 at 0. And 0 is a more simple number to work with than pi, so I'm going to work with 0. Okay, so without a transformation, cotangent's first asymptote is at 0. We do have transformations, so let's see if it changes it. Step 3. We're going to apply, I'm just going to say horizontal transformations. So on step 3, I'm going to take my value 0. And again, even though it's y on the bottom here, that doesn't matter. You start with x equals 0. All these asymptotes are x equals the equation. You start with that, x equals this 0. And then you ask yourself, is there any horizontal transformations? Yes, it's saying to multiply by 2. What's the opposite of multiplying by 2? So I would divide this by 2. What is 0 divided by 2? 0. So the first asymptote should be at 0. On your notes, the textbook did not include it. I'm going to. This is the first asymptote. That is x equals 0. That's our first one. There it is. Now to find the other asymptotes. Your other asymptotes, what value do you always start with? You start with, I heard y and I heard x. It's pi. You start with pi and you just apply the b. That's all you do. So that is a b. It says to multiply by 2. What are we actually doing then if we're not multiplying? You divide it because it's a liar. So when you put step 3 and 4 together, you have your answer. Again, this will have one extra step. So I'm going to say 0 plus n pi over 2. But if you're ever adding by 0, do you actually have to put the 0 if you're adding by it? No. So we'll just write our answer this time as n pi over 2, comma, where n is an integer. N is an integer. That's your answer right there. So that means this asymptote would be, since it's the first one to the right, it would be 1 pi over 2. This asymptote right here would be 1 pi over 2. I'm going to go ahead and put a 1 there just so you can see n is 1. That's the first one over. 1 pi over 2. This asymptote right here would be 2 pi over 2, which certainly you could reduce them and rewrite that as pi over 2 and this as pi. But you notice that's what all that's happening. This would be where n is -1. X equals -1 pi over 2. That's where all these other asymptotes are coming from. All right, your turn. Let's do the DOL number 3. So you now know the math. Pause the video and solve this one. All right, let's look at cosecant and secant. These graphs, if I haven't shown you already, they look like parabolas. Have I already shown you this class? No. Okay, let me go over here. Leave that off just in case I need it. So I want to show you sine compared to its reciprocal cosecant. Here's how these work. Here are these two. These are the two reciprocal functions of sine, and this is like the cosine. This is the sine family. Sorry, sine and cosecant are the sine family. Notice that secant and cosecant are both going to look like a set of parabolas. Where cosecant hits its minimum, where this hits its minimum, sine will be happening to hit its maximum. Where cosecant hits its maximum, sine hits its minimum. The same would be true with when you look at cosine and secant, same way. Cosecant or secant would be parabolas, and the minimum of one is the maximum of the other. That's how those work. Again, those are reciprocal functions, if you remember that. That means 1 over. So if I did 1 over cosecant, watch this. 1 divided by cosecant, check out what happens to my graph. It froze on me, it looks like. It's too complex to copy and paste, apparently. I'm just going to delete it this time, try to copy it. How about that? CSCX, what happens? CSCX, what happens to my graph? Yeah, because like I said, they're reciprocals. That's all it is. It's reciprocal. I could do 1 over sine and I get cosecant. So anyways, there are those. Let's get going on this. So solving this one. Same stuff. So here, vertical asymptotes and sketch the graph of negative secant 2. I got a question. I have a negative value in the front. Will that have any effect on my asymptotes? No, because that's a vertical transformation that won't affect whether or not my asymptote still goes from forever up to forever down. That'll have no effect. So let's go through our steps. Step 1, our trig function. What's our trig function this time? I hear h over x and h over y. Check your cheat sheet. What is it? H over x. Whoops. I can't even write it correctly. H divided by x. Great. That's step 1. Step 2. What do we have to determine on step 2? Okay, where does x equal 0? Y'all are correct. You look over here. Secant is h over x and it's pi over 2. That's correct. So step 3.
divided by 2, or pi over 2 divided by 2.
So we're gonna have x equals pi over 2. And then you apply any horizontal transformations, which in this case, I'm multiplying by 2. What's the opposite of multiplying by 2? Okay, I already have division, so I'm just going to extend my denominator and divide by another 2. I was dividing by 2, now I'm dividing by another 2. That's equivalent to dividing by 4. So the first occurs at pi over 4. That's right here. That's pi divided by 4. That's the first occurring asymptote. And then after, so even with secant and cosecant, though their periods are 2 pi, it's true that their periods 2 pi. This will still be a pi for step number 4 to begin with, because even though it takes 2 pi to complete both of these, there's an asymptote halfway between them. So every pi without a transformation, you'll still have an asymptote. So you start with pi, and then if you do have a horizontal, you'll apply the horizontal. This says multiply by 2. What's the opposite of multiplying by 2? Divide by 2. So our answer when we put it together is the first asymptote is at pi over 4. All others, and I mean all others by that n, all others occur pi over 2 units away. Some amount of pi over 2 units away is where all others would occur. There's part A. Let's take a look at B. This time, what's my trig function? CSC, I'm hearing h over y. It's right there on the right side of my screen. I agree. H divided by y. Step 2, where does y equal 0? Y does equal 0 at 0. That's right here. 0 at 0. Step 3. You would say x equals 0. And then if it has a horizontal transformation, you apply it. This says to add pi over 3. What should we do then? Minus pi over 3. I have 0 minus pi over 3. That can simplify to be negative pi over 3. That's our first transformation right here. Negative pi divided by 3. Finally, fourth step. You always take pi and you apply your b transformation. This is c. This has no b, or the b is 1. So it's just a pi. So that the c has no effect on this. So it'd be plus n pi, where n is an integer. That would be your answer again. So now that you've seen that, you can do your DOL for number 4. All right, let's take a look at some applications of this. On example 5, we want to know the damping factor. So you might be thinking, what the heck is a damping factor? Well, the damping factor is basically in the place of what I've been skipping this whole time, a vertical transformation out in the front. And this right here would be the damping factor, this x divided by 2. That right there is the damping factor. So what do we mean by this? Well, basically, this means you have a function, a trigonometric function, and it's going to get closer and closer or spread apart from the x-axis. So here's the damping factor. I'm going to write this down, and then I'm going to show you the graphs. So the damping factor is x divided by 2. So when I take out a graph here, let me just clear all this off. We're going to go ahead and graph this. Y equals x divided by 2 times sine x, I believe is what it was. Yep. And it says use a graphing calculator to graph f of x, negative f of x, and then get the function in the same viewing window. Describe the behavior of the graph. So we want to graph this, and not only do we want to graph this, let me rename it f of x like they did. What I'm also going to graph, it said, is negative f of x. So there's negative f of x. And I'm going to change colors so you can see the difference in the two. And you can see how the negative is just a vertical transformation like we've talked about. So there's f of x and negative f of x like I mentioned. But what I want to show you is the damping factor in particular. What that is, if I graphed here y equals x divided by 2, I want you to see how this corresponds. So there's negative y equals x divided by 2. And I'm also going to graph here. I'm going to copy this and I'm going to do negative. And I want you to see how the damping factor works. And so this graph happens to the damping factor as the graph, it expands away from, it's getting further and further away from the x-axis. It's oscillating as the word, but it's increasing its oscillation away from the x-axis. So oscillating just means the graph is going back and forth, increasing, decreasing, increasing, decreasing, and spreading out. So there's the idea of what we're doing. And for the future, I'm going to make this one these dotted line or dashed lines, so you can see the 2 in there. They asked me to graph the negative in there, which I think that's kind of cool, but there that is. I'll graph it like that. I want to put it on our notes. So let me go ahead and add all this in. So we'll have that for later. It'll be helpful, I think. And so you can see that behavior oscillating back and forth like it describes, like it wants it to. By the way, this, if you were writing out limits, you would not write a limit on it, anything that's oscillating, because it's not as you go to the right forever. It's neither increasing nor decreasing. It's going back and forth. So it's oscillating. Make sure I spell this right, but I think it's O-S-C-L, like this, oscillating behavior. It just means it's going back and forth, increasing, decreasing, increasing, decreasing. Okay, so there's part A. And let's see what part B says. Oh, it's just a new function. So here we go again. If we want to know the damping factor, it's the value in front of the trig function, damping factor, or it could come after the trig function for that case, but it's either way, it's the part that's not a part of the trigonometric function. So the damping factor here is x squared. So this time, what I'm going to do is I'll graph these. So we have x squared times cosine x is, I believe, how they had it. Cosine x like that. And there's the negative. And this time I want you to look at x squared and negative x squared. And so this time you can see how this graph, as I zoom out, it's getting tough to see quickly, but you can, do it. I got an idea. I want to change the y's, but not the x's. I want the y's to be a whole lot larger. Let's go negative 130 and positive 130. So you can kind of see what's happening here. And I might just zoom out one time. There we go. That's the idea of what's happening this time. So I cut that in for our notes. Again, it's oscillating because sine and cosine, they oscillate. They go back and forth, up and down. So that's what we see occurring on this image here. So it has oscillating behavior. I don't know if I actually turned on the negative, but there it would be. Which again, it's kind of neat to look at, but yeah, it's just a lot going on. So again, oscillating behavior. So it says describe, that is oscillating behavior. It's neither increasing nor increasing consistently. It's going back and forth, oscillating. All right, so here, I want you to find the damping factor of this equation. All right, I think that's enough time. So now let's take a look at harmonic damping or damped harmonic motion. So if you think about musicians, they play with harmony, things like that. What might happen if you think of like a guitar string, someone picks up their finger with the string and lets it go and it starts to vibrate. And over time, it stops vibrating. It stops making noise. But this is the idea. It's plucked and then it's let go of, and it gets closer and closer to the x-axis. It's damped going down. So it's harmonic when the function follows this. When the damping factor is k times e to the power of negative ct. Okay, so that's quite a formula right there. And you can look at these. It's crazy stuff going on right there. But that's the equation where if you had harmonic music going on, what would be going, the mathematical equation going on would follow that. So here it says a guitar string is plucked at a distance of 0.95 centimeters above its rest position. That's talking to you about the amplitude. Okay, so what we know right there is that the A is 0.95. And then it's causing a vibration. The damping constant for the string is 1.3. So when you come back over here, the damping constant is, so they told us the K right there on our problem. That's the K. I put it as A. On this problem, it's going to be K. It might just be helpful if I just copied and pasted this. Let me clear this ink, delete this. And I'm going to just copy this right here. I think this will help us so we can look side by side at what we're doing. Okay, so that's the K. K is the displacement, and that's how much it's changed. That's the K. Then we have a damping constant for the string is 1.3. And so C is the damping constant. So blue was the displacement. What I did, I'll do C in red. C is the damping constant. There we go. So C is 1.3. And it says the note produced has a frequency. Okay, you remember frequency? Frequency came from the formula B divided by 2 pi. B divided by 2 pi is 200 cycles per second. And so I could solve for my B here just by doing the opposites. This says divide by 2 pi. I'm going to multiply by 2 pi. So we can find out that the B value here is 400 pi. All right, write a trigonometric function that models the motion of the string. Okay, I'm going to assume also this is a cosine because we're going to start at its maximum. That's where you pluck it, and cosine starts at its maximum. So remember the old function I gave you last class was this: y equals a cosine bx plus c in the parentheses and then d on the outside. Well, here what we have is we're not going to have any vertical shift, no vertical shift. And so what I can plug in is that A is going to be replaced right here. We're going to say y equals, we know K, 0.95. E to the power of, this is negative, and then the 1.3 T. Now, T is just time. And so this, for a function, that's going to be our variable there. Times, and then we're going to have cosine. And so they have the W is the period. I guess if I was finding period, I should have flipped this around. So once I know period, so here's what I think this is messed up. I think what I'm going to do here is put in the B, because I think it's going to be confusing if I don't. It's 400 pi. And I'm going to check to make sure this is correct. 400 B, and then again a T for my variable inside. So they call W omega here the period, but I think B, that is actually the B value. And so I'm going to change this to omega for this problem. That's the W. Like that. And so I believe that's going to be my answer. I'm going to check it real quick and I'll come back on if I'm incorrect in saying that. Yeah, I checked it. This is correct. So they have a typo here. Omega is not necessarily the period. This would be like the horizontal stretch or shrink. And so that's not correct saying that. Horizontal stretch or shrink. It's the B value. What we normally would consider the B. Okay, so on this problem here, we did do that correctly. And so if you needed to know the period, you take the reciprocal. So it'd be 1 over 200 here. And that's what would be the reciprocal of 200, be 1 over 200. So that would be the period. Okay, so part B. So let's see, we're working through this. It has the same initial information. Determine the amount of time that it takes for the string to be damped so that y is in between these two values. So here's what I'm gonna do. I'm gonna come over to our graph and we're gonna graph what we got as our answer. So we had 0.95. I wanna make sure I don't type this in incorrectly. So let me go to the previous slide here. So I type this in and oh wait, it's way over there. Let me just copy and paste, it'll be easier. So I'm gonna take this equation, this whole equation right here, and we're gonna graph this. Okay, so I have 0.95 e to the power of negative 1.3 t times the cosine. You don't have to put this parentheses, but I will. 400 pi t. And I don't need this one, f of t right there. I'm gonna hit the home screen. I don't need that. And the damping factor, if we wanted to look at that, would be this value and this value. Okay, so now I'm gonna kind of zoom in on this so I can, let me change the x values. The x's just need to be going a whole lot quicker. So I need to make this smaller. Let me just do 0.5, 0.5, and it's still too wide. Let me go 2.5 and 2.5 like that. Okay, so you can kind of see it oscillating back and forth. What we want to know is when do the y values actually go between these two values. So we want to check between y equals 0.38 and y equals negative 0.38. We want to know when those intersect. And so as I zoom out here, I see the values intersect. It looks like there, and turn these two off just for a moment. It looks like the two graphs intersect somewhere in between these 2 points. Oops. Come on now. That one and here, this one, between those 2 points. That's where I'm getting these two values to intersect. So that's how much time it takes to have them reach that point right there. So let me copy this. I'll explain it over here to get the correct answer. So for how much time, the problem says, we want to determine the amount of time it takes the string to be damped so that the value, the y value, is in between these two values. And it looks like to me to get between those two between, did I not even type that in right? But oh, that's the x. I'm sorry. But here's the y. To be in between those two values, the amount of time that it takes is approximately 0.7 of a second, because we're in units here as a second. So it takes approximately 7.7 seconds for the values to be damped to where they're in between those two numbers. And I just took this one because it was smaller, and it's approximately 0.7. So after approximately 0.7 of a second, you are damped within those values. All right, so your turn. You can try this one. Just pause your video, find your equation to get your solution. All right, let's take a look at how we're going to finish this up. The graph of secant is shown on the domain from 0 to 2.5 pi, as shown. Notice we have 3 asymptotes. Explain why the vertical asymptotes will occur at these values. Well, this is easy. We know already about secant is step 1 here. Secant is h over x. So I'm going to write that down here and just kind of label my steps as I go. Step 1, we know that secant is h divided by x. And step 2, we could determine where x equals 0. X would equal 0 at, oops, that's on the at sign. Let me try that again. At, when we look over here, x equals 0 at pi over 2. Now, step 3 would be to apply any transformations, but there is no horizontal transformations because this has no transformations, period. No horizontal transformations. So I don't have to do anything there other than to say x will equal pi over 2. Nothing else happens to that. It's an ugly no. Let me try that again. No horizontal transformations. Okay, and so step 4 then, you would take your pi and divide it by b. Well, there is no b. The b is 1. So it's just pi. And so when we put our answer together, it would be at every pi over 2 plus n pi. Again, where n is an integer. So that would be our equation that would find all of r. So we have, it just says take half a pi and then add a whole pi. So half pi, 1 half pi, 2 half pies, and so on. That would work all the way through. That would find all your transformations. Okay, as I was saying, they're going to occur at The first one's at half a pi, and then 1 pi, 1.5 pi, 2.5 pi, and so on, because it's just adding a pi each time. Okay, here's the next question. Would the graph of tangent x and have the same vertical asymptote as secant x? Why or why not? Well, to determine that, just look at what tangent is compared to secant. Tangent, according to the cheat sheet, tangent is y over x, and secant is h over x. So what gives you a vertical asymptote is dividing by 0. Notice these are the same values. So since they're both x, they would both be having asymptotes at the same time. Yes, these would have the same vertical asymptotes because we're dividing by the same variable x. So they would occur at the same spots. Whereas, in contrast, cosecant and cotangent, these two would have with one another, cosecant and cotangent would have identical placements for their vertical asymptotes. However, they would be different from secant and tangent because those secant and tangent divide by x, cosecant, cotangent divide by y.